Hello, welcome to my video on data structures. In this module, I will talk about the topics that we will learn for each individual data structure through a very simple example. Recall that data structure is the study of data storage, management, and access. These are also the major topics that we will discuss when learning a new data structure. Let's begin with data storage. First, we want to know how the data structure stores the data internally. For example, whether it stores the data as a continuous array, as individual blocks that are linked by pointers, or in other forms. Understanding the internal storage is key as it will determine many of the data management and access operations. Second, we want to know how the internal storage scales when we are given a large volume of data. Here, we will describe the scalability as space complexity, which shares a similar idea as time complexity, or the big O notation you might be familiar with. All right, let's move on to the data management and access. Here, we are interested in 3 points. First, we will discuss what types of operations does the data structure support. For example, whether a data structure supports the deletion of an arbitrary piece of data, or whether it can tell the size of data it stores. Defining these operations is similar to defining the interfaces of functions, and we just need to specify the expected inputs and outputs. We also refer to these interfaces as the abstracted data type, or ADT, which describes the expected behavior of the operations that the data structure supports. Second, we need to study how each operation is actually performed. That is, we will study the set of well-defined steps that ensure each operation is properly performed. Third, we will investigate the scalability of these operations by looking at their time complexity. And finally, we will go over the implementation details of data storage, as well as the data management and access operations. While the examples will be primarily written in C++, you should still be able to get the key idea if you are using other programming languages. Now, I want to illustrate the idea we have discussed above using a very simple example. Imagine that we are interested in developing a data structure to hold a single integer number. Let's begin with data storage. Since we only need to hold a single integer number, we can just use a single variable to store the data internally. And it is easy to see that the space complexity is constant, or O1. For data management and access, let's begin with defining the ADT. We'd expect that our data structure will support 3 operations. We will describe these operations as functions in programming languages. The first function, is empty, should tell us whether any piece of data is being stored. It should return true if no data stored and false otherwise. The second one, insert, should record the integer number VAL, which is given as the input. We want this function to return true if the value is successfully stored, or false otherwise. If there's no data being stored when the function is called, then we are fine. However, what should we do if there has been some data already? A safer choice that can prevent accidental overwriting is to prevent the data insertion and simply return false in this case. The third function, is even, is expected to check whether the stored integer is even. In case of no data stored, we will have it return false. Now, let's see how to implement these functions. First, to implement isEmpty, we need to know whether the function insert has been called. Because if insert has been called, then we would expect some data is stored. In this case, we will introduce a tag variable, which will be set when insert is called successfully. And we will simply check the tag variable when the function isEmpty is called. Second, for insert, we will first call isEmpty to check whether any piece of data has been stored. If yes, we return false immediately as we do not allow overwriting data. Otherwise, we will try to store the data value. If successful, return true. Otherwise, return false. Third, for the function isEven, we again will first check isEmpty to determine whether any piece of data has been stored. If no, return false. Otherwise, we will compute the remainder of the stored integer when divided by 2. We will then return true if the remainder is 0 and false otherwise. Now, let's look at the time complexity for these three functions. For isEmpty, as we only need to check the tag variable, therefore, the function can be done in constant time O1. For insert, we will need to first call the function isEmpty and then perform a data assignment step and a tag setting step. All steps can be done in constant time O1, so as the entire function. For isEven, we will also need to first call the function isEmpty and then perform a remainder calculation. Both steps can be done in constant time O1, so as the entire function. Now, let's move on to the implementation. And first, look at the data storage part. We will use two variables for this data structure. The first variable, data, stores the integer value. The second variable, isEmpty, is the tag variable that records whether any data has been inserted. For the implementation of isEmpty, we simply return the tag variable. For insert, we first call isEmpty to check whether some data has been stored. If no data stored, we will try to store the integer val. We will further determine whether the insertion is successful by checking whether the data that has been stored is the same as the data we need to store. If the insertion is successful, we will notify our tag variable that the data structure is no longer empty and return true. For isEven, we will also call isEmpty first and return false if no data stored. Otherwise, we will calculate the remainder of the stored integer when divided by 2. If the remainder is 0, then the highlighted expression will evaluate to 1, which indicates a return value of true. Otherwise, the function will return false. Now, let's check whether our implementation behaves as expected. Here, we will perform 4 steps with our data structure. First, we will initialize an instance of the data structure and check whether the initialized instance is empty. Second, we will insert an integer 56 and check whether the insertion is successful. Third, we will check whether the data being stored, which is expected to be 56, is even. Finally, we will try to override the existing data with another integer 73 and check whether our data structure allows us to do so. Here is the output of our implementation. The first line suggests that the initialized instance is empty. The second line suggests that the integer 56 is successfully recorded. The third line indicates that 56 is even, and the fourth line indicates that our data structure does not allow us to override data. The output is consistent with our expectations of the data structure. At last, we summarize what we have learned in this video. For each data structure, we will focus on studying three aspects. The first one is data storage. We care about how the data is stored internally and how the storage scales with the data volume. Second, we also need to study the data management and access operations. We will need to know their inputs and outputs, detailed steps, and efficiency. Finally, we should also be able to implement data structure with the above knowledge. All right, that's all for this video. Thank you for watching and see you next time.